morning, everyone. Thanks for joining the INCITE webinar. And today I will be talking about innovations at the interface of fermentation technology and green chemistry. So first of all, I would like to present a little bit the framework of the work we are doing. And the work is really aiming at facilitating the transition from a fossil resources-based economy to a bioeconomy that is based on renewable resources. As you all know, most of the materials and the fuels that we're using today are based on the use of fossil resources with all the problems associated with that, the limited availability, the impact on the emission of CO2, which leads to global warming. And this is because the CO2 that was used to produce the fossil fuels has been in the soil for millions of years and which is now coming into the atmosphere. So it is a cyclic process, but a cyclic process over millions of years. And that's, of course, not what we really want. We want to a circular economy with carbon dioxide going through the system in 1 year or a number of years. And therefore, we are trying to use bio-based resources based on plants, animals, but also looking at waste streams of the food industry, of the agricultural industry. And in this way, we are trying to lower the ecological footprint of the production of chemicals and materials. What are the challenges here? So the way we want to do that is, of course, because we want to use or to develop biorefineries where biomass, plants, waste streams, and animal products are transformed and refined into a set of molecules that are bio-based, and then upon modification or directly we can go to materials and chemicals. There are some opportunities. There is a lot of pressure now from the governments and from the EU to try to facilitate this transition. We have the REACH regulation, which is the registration of chemicals, and that means that some of the more toxic chemicals will be banned in the future. So there we need to try to find alternatives, and one of the ways to do that is to use renewables. We have also the European Green Deal that is really pushing towards this transition. But on the other hand, trying to go to this bio-based economy also results in a lot of challenges. First of all, production price can be quite high if we think about certain crops where we need to isolate the compounds of interest that can lead to severe costs of separation. Also, there is an issue about transportation of biomass, because in a number of cases we need to transport a lot of water. So you need to first try to concentrate the biomass into a source that is more dense so that you can reduce the transportation costs. And of course, you have the seasonal availability, because if you want to work with industrial crops, it means that you are linked to a certain harvesting period, but also problems because of the climate and the weather that can be different, the soil can be different. That means that the quality of the products can be quite variable, and that poses a lot of problems to use these products in industrial processes. So as we speak, this transition to a bio-based economy is still quite slow. And if we look at the chemical industry, then we see that in Europe and the US, more or less 8 to 10% of the chemicals that we're using are now bio-based. So that means that this transition will take a number of decades in order to try to improve that number and have more bio-based chemicals on the market. Also, we have to think about the approach that we want to use, because that could be very difficult. When we think about petrochemistry, then it's normal that we start from crude oil and that we are going to crack the crude oil in a petrochemical refinery to a number of building blocks that have a very low molecular weight. We think about ethylene, about propylene, butadiene, toluene, benzene, and so on. And from these unfunctionalized molecules, we need to build up to increase complexity in order to make materials. We could think about doing that also in the bio-based economy. And for a number of sources, we are doing this. So we start from biomass and we crack or we ferment the biomass to simple molecules, being gases or being ethanol, for example, that can be used as a biofuel, or ethanol can then be turned into ethylene. And then, of course, we can use the routes that have been developed during from petrochemical sources. So then we have a kind of drop-in chemicals that we can use. Another strategy, and to my idea, a much more clever way of doing, is to try to utilize the complex molecules that are made by nature by a big set of enzymes in plants, and not to break down this complex structure and then build up again the molecular structure, but try to isolate these complex molecules and use these in order to develop new applications, new biological active products, and so on. Of course, this approach is not possible for all the materials and all the chemicals. In some ways, we will have to break down and build up again, but wherever possible, I think it's a smart idea to isolate the complex molecules from nature and then use these to transform into active products. And that's why we are looking in our laboratory to really marriage the fermentation technology, which is done by one of my colleagues, and the green chemistry that we are developing in our lab. I'm convinced that the interface between fermentation and chemistry, that there are still a lot of opportunities to develop processes and materials that can be very interesting. Before, let's say 20 years ago, the people were thinking in the way either completely doing fermentation technology or completely doing chemistry, but I think on this interface, there are still a lot of opportunities, and that's one example that I will discuss today about this marriage between fermentation technology and green chemistry. So the case that I want to present today is the use of sofrolipids, and that is the molecules you see here centrally. It's a quite complex molecule that is built up of 2 glucose units and which is connected with a fatty acid molecule into a lactone. This is quite complex, and it gets produced by a non-pathogenic yeast, Starmarella bombicola. And at the moment, this sofrolipid is already on the market. I will come back to that later on. But you can produce it with a quite high production quantity, with about 400 grams per liter in the fermentation broth. It has a number of biological activities, so it makes it interesting to look at it more closely. And then one drawback, of course, is its high production cost at the moment, 2 to 5 euro per kilogram, which is quite high for such a molecule. And of course, that's why we are looking at applications in high value added domains, because you need to be able to use these molecules with this quite high starting price from the fermentation. So I'm not going into the details of the fermentation and the formation of the sofrolipids in the yeast, in this yeast Starmarella bombicola, but just a few aspects. Stalmarella bombicola is using oleic acid, a C18 fatty acid, and through a number of enzymatic steps, glucose is added to the fatty acid. In the second step, a second glucose unit is added, and then finally, upon lactonization, you get the sofrolipid. And as you see here at the bottom of the slide, you have some sofrolipids that are acetylated, so where the OH groups are protected, and also you can have the free OH groups. So in the fermentation broth, we get a mixture of compounds, but mostly we get the major product, which is the first one. So that's the first challenge. If we want to use these molecules, we need to be able to start from pure molecules. We have to do a cleanup of the fermentation broth to get to the sofrolipid. One important aspect is the fact that here the yeast is starting from oleic acid, and it's very limited in the number of fatty acids that can be used. So the yeast can use a C18, a C16, but that's about it. You cannot change the chain length of the fatty acid too much, because then the yeast will not grow. And so that limits the number of sofrolipids that you can produce by fermentation. And so it also limits the amount of application. And that's why we want to use green chemistry to make a whole library of sofrolipid derivatives and to look into the applications of these new molecules. So sofrolipids have a number of very interesting activities which are known and which are in the literature, and for which some of the products are already used. They have a very positive dermatological profile. They have some antimicrobial activity, some anti-cancer activity, and also some antiviral and spermicidal activity. On top of that, it also forms some nanostructures in solution, and it can also be used for the capping of nanoparticles. So because of all these aspects, we felt that trying to extend the number of sofrolipids would be very interesting, and also then to be able to screen the activity in a number of different domains. And I will talk about two domains that we have been looking at. So as said, the sofrolipids are already on the market, mostly in detergent type applications. You have the sofrose unit, the two glucose units, which are of course hydrophilic. You have the fatty acid chain, which is hydrophobic, and of course the combination leads to detergent type activity. So these products are on the market in some detergents. For example, in Belgium, Ecover is a company that markets this detergent, but they are also present in cosmetics, and also Saraya is a company that brings these products onto the market. So the sofrolipids itself, as they are produced by fermentation, are already marketed. But we want to see if we can go a step further. So what are the possibilities here? If we look at the structure, and here this is not the lactonic form, but the open form after hydrolysis, you see that you have actually three domains where you can interact and where you can do some chemistry. You have the sofrose units with the sugar moiety, you have the double bond, and you have the carboxylic acid function. And we first concentrate on the double bond because we want to functionalize and try to develop some functional intermediates that will give us a possibility to prove, oh, this is not going well here. Let me go back. So that we get an intermediate that allows us to produce a whole set of intermediates. So the principal idea that we had is to do an ozonization reaction on the double bond, which would create two aldehyde functions on the sofrolipid. And so this aldehyde function would then allow us to do a lot of chemistry. We can go easily to the carboxylic acid, we can go to reduce it to the alcohol, but we can also use it as an aldehyde, and then try to introduce some functional groups, looking at high-value applications, and especially we're looking at pharmaceutical or biomedical applications. So here is the outline. So we want to purify the sofrolipid from fermentation. We will do the ozonolysis of the product to the intermediate, and then we will try to come up with some straightforward chemistry to introduce some nitrogen. And I will explain in a minute why we are interested in these nitrogen containing compounds, and then finally working together with different laboratories, we will also determine the biological activity. So we started off now. We will get a number of very chemical slides, but I will try to not to go into detail and to go over it quickly. I think it's more important to get the philosophy that we were following and not going into the details of the chemistry. So as said, our first step is a reaction with ozone. It's an oxidation, but ozone is a very clean oxidation. Of course, we have to take care of some dangers using ozone, but we were quite, this is quite easily done. And that gives us an intermediate here centrally with an aldehyde function, and then also a second part here. And upon hydrolysis or upon a reaction with the base, in this case a methoxide, we were planning to get two important building blocks that we could use as a bio-based building block. Unfortunately, this didn't go well, and we got a number of problems with the purification, and also the fact that this C9 building block really led to the dimerization by an aldol condensation, and that really complicated the story. So we gave up on that one. We had to come up with a new approach, and the new approach was first to open up the lactone ring. I'm sorry, because it jumps here, to open up the lactone ring to get here the methyl ester, and then in the second case trying to do the ozonization, but this time we were trying to do this in methanol, and you do a reduction and then you get the aldehyde, but unfortunately here we got also the acetal, so also here we were having quite some problems. So as said in the beginning, the yeast can only use a very limited number of fatty acids, and to have also some variation on that, we also used for the fermentation petroselenic acid. So that was done by my colleague, Professor Soutard, who is an expert in biotech and in fermentation technology. And they used this petroselenic acid, which we isolated from coriander plant. And you can get this from the oil. It's an easy process because this petroselenic acid is present in about 70% in this oil. And so that gave us also sofrolipids, but now with the double bond at another position. So that would give us also aldehydes now here with a different chain length. So also by using this petroselenic acid, we could introduce some variation in the aldehydes that we could produce. For these sofrolipids, the surface tension didn't change much, but the critical micelle concentration, however, is very different between the sofrolipids based on the petroselenic acid or based on the oleic acid. So finally, after quite some work and after doing a lot of discussions with our colleagues from biotech, they were able to genetically modify the Spermarella bombicola to produce these type of sofrolipids. As you see now, you have here the fatty acid chain based from or coming from oleic acid, but now we have two sofrose units that are linked to this fatty acid. And by doing this, that really changed our world, our life, because now if you do the ozonization and you cut the double bond, you get two pieces which are identical. And by doing this, that really improved the separation of these products from our reaction on the ozonolysis. So that really made our life much easier. And so we could do that in reactions on 40 grams per liter with the pH control by phosphate buffer. We were able to isolate easily these kind of intermediates now that are ready to get transformed. And here, I don't want to go into much detail, but one of the reactions that we are using, a very straightforward reaction, is a reductive amination. So you use a secondary amine to form the corresponding imine, which you immediately reduce, and you get the corresponding aminated products, which we could have in reasonable yields. The yields are about 50%, and that was also due to some separation problems. These are not easy products to purify because they start foaming and so on. So it takes some time to find the right methods to purify these compounds. Of course, on the bottom of the slide, if we use a primary amine, we can either produce here the secondary amine derivative, and if we use very little of the amine, for example, only half equivalent, of course, then this amine can react twice and we get the dimeric type of compounds. Now, what did we want to do, or why did we want to have nitrogen in the molecule? And that was because we wanted to make cationic derivatives. So now with this amino group, we can easily methylate or alkylate this by using alkyl iodides, for example, methyl iodide. And now we get the positive charge on the nitrogen. And it's known that a lot of these positive or these quaternary ammonium salts have a good biological activity as an antimicrobial compound. And that was the application that we were after in the beginning. And of course, in a second step, we can deprotect the acetate function to have also the free hydroxy groups. Now, we wanted to check this, and here we analyzed the biological activity against a number of bacteria, a number of gram-positive, Staphylococcus and Bacillus, also a number of gram-negative, Escherichia and Klebsiella, and then we looked at the activity and the minimal inhibition concentration. And this was the result. Again, we could detect a number of very active compounds, especially the one with the C18 group on the nitrogen and the positive charge. They are listed there. We had 4 compounds that were highly active, and they were even more active than gentamicin sulfate, which was used as a benchmark in this kind of biological testing. But of course, not all compounds were a success. Another way we tried to introduce a positive charge was to form the amino oxides, and that was easily done by treating the amines with a perbenzoic acid to give the corresponding amino oxide. And also here we can do the deprotection of the acetate function on the sugar. But for these compounds, we could not find any activity at all. So these compounds are not active, and that was a little bit disappointing for us. But okay, it's not always the case that we get some activity here. Of course, now that we had the aldehyde in a pure form, now we can start playing with a number of reductive amination steps. We can use here a diamine to form the kind of bola form sofrolipid amines with now 2 nitrogens and a central unit. I'm sorry, but it keeps jumping here. Or we can use a primary amine, and then, of course, you get only 1 nitrogen between the 2 sofrose units. And again, here we can do the quaternary, the formation of the quaternary ammonium salts. We can do it directly on the protected derivative and then do the hydrolysis, or we can also do the hydrolysis not to have the quaternary ammonium salts. And you feel that by the simple reductive amination on different type of amines, we were able to produce a whole library of different compounds. So here again, we can either do the hydrolysis of the acetate functions, or we can also do for these compounds with 1 nitrogen in the central chain, we can again do the quaternarization and then the hydrolysis. So the philosophy of synthesis was kept the same here. And also here, looking at these bola form sofrolipids, again, we could find some quite active compounds. And so here we get to activity in the range of about 40 to 70 microgram per milliliter, which gave quite nice activity. And we will be working further on that to see if we can use these type of applications to put this in an application so we can have this detergent type of activity combined with the antimicrobial activity of the compounds. And to wrap up my presentation, I want to briefly also talk about a second type of activity, and this is on transfection. So if you want to put DNA or plasmid DNA into cells, there are a number of technologies. One is to connect the DNA to gold particles and inject these gold particles into cells. But of course, the drawback of this method is that a lot of cells die because of the damage of breaking the cell wall. Another way is to put the plasmid DNA into a kind of a detergent molecule, so we get a kind of a phospholipid particle, and then we can move that into the cells. We have tested a number of our sofrolipids, and here we had 2 which were reasonably in the activity, but they were not more active than the compounds that are now being used today. These cationic lipids that are now used for this application are cheaper, and we didn't have an improved activity. So we have to look further into this application. I will not go through all the details of these graphs, but we have been able to prove that indeed the plasmid DNA gets into the cells, but the efficiency was not much better than the solutions, the cationic lipids that are used today. So I hope I have been able to convince you that combining fermentation technology with green chemistry gives you an opportunity to really expand the number of compounds in a very easy way with just 2 reactions with ozone to cut the double bond, and then reductive amination in a 1-pot setup. We have been able to produce a complete library of different compounds where you have bola forms and normal molecules that have been tested then on the antimicrobial activity and also the transfection efficiency. And we are now looking to extend this, this chemistry on the sofrolipids, trying to develop further new biological activities. So I want to thank the people working in our group, and especially the two people, Elizabeth Delbeke and Melike Pala, who have been doing their PhD on this topic, and we are further looking into the chemistry of the sofrolipids in collaboration with our colleagues of fermentation technology.